So basically, this presentation we will discuss some wireless technology that people are exploring for next generation wireless networks, especially 6G and 5G. That is the second part. So that is the outline of my presentation. We will discuss what is the wireless communication. Then this multiple access technique, that is also a research area in the wireless network currently. That we will also discuss. Then this intelligent reflecting surface, people call it as IRS. So that briefly we will look. Then terahertz communication. What is the terahertz communication? And joint sensing and communication, and orthogonal time frequency space modulation, and deep learning for wireless communication systems. So this brief of this technology we will discuss in the presentation. So that is the these are the some application of wireless network. If you see the autonomous vehicles, vehicle to everything, then brain computer interface, remote surgery and tactile internet, space terrestrial integrated network. These are the new applications people are looking other than the conventional applications that we have currently. Okay, so especially this non-terrestrial network, that is very important area. People are looking for 6G. Okay, currently you can see that when you just in the air, that internet connectivity is there. So that is terrestrial and non-terrestrial, especially satellite communication. So people are trying to integrate that technology, so you can stay all the time throughout the internet. Okay. So integrated terrestrial and non-terrestrial network, that is another aspect people are looking. Then you look at smart city. Smart cities meaning is like some application of wireless technology people are looking. Okay, for network trafficking management and waste management, healthcare, all these things. Then swarm robotics. So that is another application. Like you have robotics. So robotics are connected through the terrestrial and non-terrestrial network, especially if you're looking at defense application. So you have a robots, and robots are not only connected to your base station or mobile, they are connected also to satellite also. So integrated connectivity on the robots. Okay. Then digital twins and metaverse. So currently people start talking about virtual world. Okay, so virtual world, you see that a digital twins and metaverse. So that is a part of wireless. Wireless body area network. So healthcare people are talking about wireless. Then wireless sensing and environmental monitoring. Sensing meaning is like you scan the environment, okay, surrounding. And so meaning is that initially we have a radar system and communication system. So radar is developed independently, communication system developed differently. Now people are talking that can be single device can work as a radar as well as communication device. Okay. That it happens in the earlier time also, but due to some limitations of the signal processing complexity of these things, it was not successful. Okay. So currently people start working in the field. Then people start also looking at quantum secure wireless networks. So that meaning is that quantum algorithms that for security in the wireless network. Okay, because what is happening currently, if you see that computational complexity, the computational power has grown up significantly. So conventional security algorithms may be not efficient. So what are people thinking? Can we have some quantum algorithm? So how they will work? What they are people thinking? You have data bits. So bits you convert into the photons or the photon states. Okay, then you put some security algorithm in there. There is a few bits. So this is the first practical wireless communication system is demonstrated by Marconi in 1894. But some people also claim that this means that this Bose is also pioneered wireless communication. So this is the wireless communication system. If you see that we have three parts. One is the modulator, another one is the wireless channel, and another one is the decoder. This part is the transmitter, and this part is the receiver. Between that, we have a wireless channel. Okay. So wireless channel meaning is that is the surrounding of us. So we cannot control the surroundings. You can design the transmitter, you can design the receiver, but we cannot control the wireless channel. They depend on the surroundings. Hills are there, buildings are there, cars are moving. So that is not in our control. Okay. So we can design transmitter and receiver. Okay. So now this wireless channel has very important parameters. Okay, important parameter is that it has some physical characteristics. Generally, we call it delay and doubler. Okay, based on that wireless channel property, we have to design transmitter and receiver. So 1G to 5G that we have reached 5G. Okay, everyone is exploiting the wireless channel. Okay, so you understand the wireless channel, then think how we design the transmitter or how we design the receiver. Okay. So especially initially we started, for example, 2G. Okay. That is a digital technology first. Earlier 1G that is analog. So 2G, what they people think wireless channel they understand in the time domain. Okay. Then they design the transmitter and the receiver. Then some people came little different idea. They understand the channel. Then they design the CDM technology, then 3G. Okay. Then we have come to OFP, orthogonal frequency division multiplexer, that is the 4G and LTE. Okay. So 4G and LTE, what people thought that initial 2G and 3G are designed by considering the wireless channel in the time domain. Okay. Then people think like understand the wireless channel in frequency domain. Same thing, but your understanding in a different domain. For example, you have a Fourier transform. So you have a time domain signal, then you have a frequency. So when you have a time domain, then you understand signal different. For example, sine wave. So sine wave, if you look in the time domain, then we understand this is continuously oscillating and having non-zero samples. You can continuously use so many samples are there. Okay. But if you take the sine wave in the frequency domain, so it is just our impulse. So you will see that sine wave is everywhere zero except one point in the frequency domain, delta. Okay. So that is our idea in how you understand the things in different domains. So earlier people understand the channel in time domain, they look 2G and 3G, that is called GSM and CDM technology. Then some people came, they understand the channel in frequency domain, then they approach like if we design the transmitter and receiver in the frequency domain point of view of channel, that will be good. Okay. So they propose a new technology that is the OFDM technology. That is the 4G and 5G, still we are using. So that wireless channel is very important. Okay. People understanding, exploring the wireless channel, then they designing the transmitter and receiver for the communication. Okay. Why we are exploring? Because the demands are coming from the various sectors. So you see, we are trying to get the high data rate. Okay, we try to minimize the latency, we try to improve the security, we try to reduce the energy, improve the energy efficiency or the spectral efficiency. So many aspects are there. Then people think if we look this approach, then maybe we can have some good parameters or that is called key performance indicators in wireless technology. So we can improve those KPIs. Okay. So that is the whole idea developing the wireless technology. So if you are just exploring here the delay spring. Delay meaning is that if you have a transmitter, you sending one pulse, but receiver you will not get only one pulse, you get copies. Why we are getting multiple copies? Does anyone have any idea? Because surroundings. So if we see that, for example, in this mode and receiver on this mode. So some signal is the signal is transmitted by antenna. So some part of signal directly go to that receiver. Some parts of the signal go then reflected. So you have a multiple paths between transmitter and receiver in the wireless communication. Okay. So if you have multiple paths, then you can see that direct path has the shortest distance and reflected path has a higher distance. So higher distance means you will reach later. Okay. So shorter distance means you will reach first. Okay. So that's why you reaching some part of signal reaching at earlier, some parts are reaching later. So you have a like a window kind of thing, response. So that is called a delay state. So you can see that a typical channel scenario, if you can see from channel, you will start receiving the signal from here and significantly more. Okay, so that is called a delay state. See the delay state here is 70 to 80 nanoseconds. Okay, so even just very small duration signal, you are getting 70 to 80 nano duration signal. Okay. So that is called a delay state. Okay. So what is the impact of delay state? If you can see impact of delay state, if you putting the one data symbol here, and if you putting another data symbol here, then you will not get any intersymbol interference. Okay. Otherwise, what will happen? You put the one data symbol here, another will be here, close to that first one. So both will overlap at the receiver side. Okay. So delay state was the intersymbol interference. Okay. So that's why we have to consider the delay state while we are designing the system. Okay. So that is to avoid the delay state, that is called intersymbol interference. Use the equalization. Okay. So equalization is a technique that can mitigate or reduce the impact of ISI at the receiver side. So one physical aspect of wireless channel is the delay state. These are the different wireless communication technologies. If you look the radio communication, so that's another type, FM or AM. Okay. So why we characterizing the wireless communication into different categories? Because each category have a different application. Okay. So for particular application, if you can design the system, that is good. Okay. For example, signal and system. When we study the signal and system, we classify the signal and systems in the different category. Why we are classifying? Because we want to visualize the things very easy. If you have a particular type, then you have a particular choice for them. So this is kind of you have some diseases. Okay. But if you know the disease, then you know the like what is the possible treatment. So same thing is happening here. If you designing the radio communication AM, you will use the different approach. Then you have a satellite communication. So satellite communication, you know that is a different parameters. Why satellite communication? Because satellite is quite far away. So you have a very large delay state. Because signal take time is there as compared to that one. Okay. Then satellite is moving very fast. So Doppler is very high. We remember that Doppler is proportional to velocity and frequency, carrier frequency. So we have to have very high delay and very high Doppler to take care of that satellite. Then Wi-Fi. Then similarly you have a cellular network. That is one of 5G we have witnessed. Bluetooth technology. Then infrared, for example, TV. Okay, so you use the visible light. Okay, that point towards the receiver side, and then communicate. Then Zigbee is again a kind of short range communication. So these are the different wireless communication. Let's understand another challenge in the wireless communication. So, for example, this is the base station, this is the wall or the building, and this is the moving car. Okay. So when car is moving towards the base station or going away from the base station, so you will also get Doppler frequency. If you remember that Doppler frequency is proportional to V1 is equal to FC V upon C. FC is the carrier frequency, V is the vehicle speed, and C is the speed of light. So when you have a high vehicle velocity, that time you have a high Doppler. If you have a high communication frequency, then you have a high Doppler frequency. Okay. So then you have another path. Okay. That is the first line of sight path, and this is called a reflected path or non-line of sight. So this is also have a Doppler frequency. Okay. So what is the delay spread? Delay spread we have defined like last path minus first path time. Similarly, Doppler spread we define like last path frequency Doppler minus first path like that. So you have a window kind of thing. So you have a two things, that is a Doppler spread and then you have a delay spread. Delay spread we have defined tau 2 minus tau. Tau 2 here is a path that this path is arriving, and tau 1 at this time this first path is arriving. So you have a delay spread, Doppler spread. I'm not going to much detail, I don't know these things. So now two parameters we have. One is the delay spread, another one is the Doppler spread. Okay. Then let's highlight what is the change happening for 5C and beyond, especially 6C. Earlier, as I pointed out, OFDM is developed, orthogonal frequency division multiplexing. That is the 4G LTE that I call 4G LTE. So they designed the channel in the frequency domain. Design means they understood the channel in frequency domain. Then they designed the transmitter and the receiver. Okay. So that time the 4G LTE especially was designed to handle the delay spread. Okay. That is a big problem with the CDMA technology. Now what is happening? We have a high moving vehicles or satellite communication. Okay. So people thinking like can we have another technology? Why? Because this Doppler spread is very okay. Because the speed is high, then carrier frequency is also high. If you remember that currently 5G phones have a frequency band above 20 gigahertz, that is around 26 gigahertz. Every phone generally have that frequency. Okay. Above 20 gigahertz. Earlier we are using what is the frequency earlier? Sub 6 gigahertz, 2 gigahertz, 3 gigahertz. Okay. So frequency, if you see the 3 gigahertz to like 26 gigahertz millimeter wave. Okay. So when frequency is high, then Doppler is also high. Okay. So now what is happening? We have a new network that can handle high Doppler and high delay. Okay. Earlier we have a delay spread, but that is less, not significant. Okay. Now we have a both delay spread and Doppler spread, and both are very significant. So we have to think differently. So currently our this 4G LTE, for example, cannot handle high Doppler. Okay. If you are going for high speed communication, you will experience that signal quality is very low. Okay. Degradation are very high. So we have to think different. So that is the motivation to develop the next generation wireless network, or you have to come up with new ideas, okay, to design transmitter and receiver. So these two physical parameters, that is a delay spread and Doppler spread, that is the inherent property of wireless signals. So we have to deal with these two. So this is the KPI, is key performance indicator of wireless network. Currently we are evaluating wireless network by considering the latency. Latency meaning is that you sending something transmitter to receiver. Okay, so you can analyze that how much time you're taking for transmitting, decoding. User density meaning is that currently everyone has a mobile phone or other devices. So connectivity, like how many devices we can connect per square kilometer. Okay. So that is the user density we have to increase. Okay. Then we have a throughput. Okay. Throughput is the kind of data rate. Okay. So data rate we have to increase. Mobility, like that network should support high speed. Okay. Then spectral efficiency. Spectral efficiency, how we define the spectral efficiency? Generally, bits per hertz. So giving the spectrum, how much data rate you can push to the network. Okay, so that is the spectral efficiency and energy efficiency. Okay. What is energy efficiency? How will define energy efficiency? Yeah, energy consumed. So like if you sending some data, for example, 1 Mbps data rate if you sending, then how much energy you are consuming? So to define that energy efficiency, data rate divided by consumed energy. Okay. Yeah. So that currently is very important. Why it is very important? Earlier time we have, for example, like 10 years before, okay, we have very less number of mobile phones, for example. So we are not worried because the mobile phone charging it will be consumed 1 watt, but it is very less. But currently you can see everyone has almost 2 phones. Okay. So even if it's consuming 1 watt, okay, then a lot of mobile phones. So this 1 watt results a big amount at the and power is generated, powerhouse. So from there you are getting 1 watt, that may be like 50 or 60. Okay. Because some losses during the transmission. So energy efficiency is also very important parameter. So these generally are the KPIs. Then you are aware of also reliability. Reliability meaning is that how you are reliable. That worst scenario is how you are covered. Okay. So that is the main reliability. So these are the KPIs, key performance indicator. By considering these KPIs, we try to evaluate a network performance. Generally, if you remember, we analyze network or some system, wireless system, by considering the data rate, bit error rate, maybe you have heard this one. Energy efficiency, spectral efficiency, and so on. Okay. Then key challenge are channel fading and path loss. Okay. What is channel fading? Channel fading means, as I pointed out, transmitter and receiver have a multiple paths. So each path is arriving at a different phase. Okay. So if you not take care of those phases, then what will happen? Signal will get consecutively or destructively. Signal strength fluctuates quite a lot. So that is called fading. Okay. So we have to take care of that one. So how to take care of that one? Each path we have to track. Each path we have to resolve. Okay. For example, 4 paths are arriving at the receiver, but you are only resolving like 2 paths. So what will happen? Fading will be there. Actually 4 paths, but we are considering only 2, but we have some limitations. So that is very crucial to handle the fading. Then loss SNR, signal to noise ratio. Interference. Interference is coming from the outbound network or inbound network. Okay. Multiple scenarios are there. Okay. So then we have a security and privacy, then mobilities. So that part we have considered while designing the network. So let me summarize what the meaning of this slide. Here we are highlighting the KPIs. So KPIs are generally, once we design the network, then let P or C will come, let how we are going. Okay, then I will say let evaluate my design by considering these KPIs. Okay, if P or C will be okay with these KPIs, then that is system is okay. Then generally we analyze this parameters, data rate, bit error rate, efficiencies, spectral efficiencies. But while designing the network, we have some issues. Issues that we take care of those issues like the fading, path loss, SNR, interference, security, and mobility. So this is the evaluation of especially the wireless standard cellular technology from 1G to 5G, then 2030 we are going over 6. Okay. So that you can see every 10 years we have a new technology with that calling G generation. Okay. So first generation started around 1970s and then that's 5G and deployed in 2020. Okay. So why we are going to next generation communication or technology every 10 years, as I pointed out, demands are coming from various sectors. Earlier, we don't have high data rate demand. When mobile phones started, that time we just use for calling. So calling, we don't have enough data rate. Okay. But currently, we are using mobile phones for multiple. So we need high data rate. So that is another parameter. That what is the parameter? We need a wireless network that provide us high data rate. Okay. Then data rate is also growing. That's no question on it because you have a lot of data. Okay. for different applications. Then, apart from the data rate, what is the application? Other demand. Massive connectivity. Massive connectivity meaning is that how many users or device you can connect per square kilometer or per square meter that we can. So massive connectivity, we have a network that can support multiple devices. For example, if you connect the this geo connection, okay, that is a broadband, okay, or Airtel. So they will give you some special you connect this much number of devices. So that you can understand that the massive connectivity. When you connect to the Wi-Fi router, they specify you can connect this much of devices. So that way we can understand the massive connectivity. So I'm not going to finish here. So these are the people looking for 6G, especially IIT 2030. Okay. So here I'm just highlighting that the three different integrated sensing and communication, integrated AI and communication, and human features connectivity. So these three things are added in 5G network to deploy or deployment or start exploring the 6G wireless technology. Okay. So I'm just highlighting here only things. For example, integrated sensing and communication. Integrated sensing and communication meaning is that, as I pointed out earlier, a single device can work for radar sensing. Radar is sensing, scanning of around. Okay. And the same device can work for the communication. Okay. Why they should work for a single device? Because earlier time people explored this. Okay, but due to some signal processing capability or device capability or computing facility we have, so we haven't reached. Okay, but currently people trying that we can have both the same device. Okay, so that is called integrated sensing and communication. Okay, what the function of the communication? We're doing detection. For example, you sending the BPSK installation. So what we will do? Given the channel and transmitted signal, we have to estimate the bits. Okay, so detection and estimation. Same thing we are doing there in radar. What the radar? If we have a target, okay, so we have to detect whether target is present or no. If present, then we have to estimate its parameter. So detection and estimation is also part of that radar. Okay, so can we have a single device that can work radar and communication? But some problems are there. Okay, what the problem? Some fundamental limits are different for communication and radar. Communication, we are putting high data rate. Okay, when you put in the high data rate, so what do you do? You use higher order modulations. Okay, we expect good SNR. Okay, but radar signal is traveling like going and coming back, so reflect. Okay, there is no receiver, so that can boost my signal. So receive signal is very deep. Okay. So that part. Okay. Another aspect is that once we have a radar and communication single device, so what you will do, you will transmit the signal for radar, and from the downlink probably scenario, that the downlink device is sending the data. So you are receiving also. Okay. So sending and receiving happens simultaneously, so interference will be high. So how will we manage that interference? Okay. So these are the issues we need to take care. Okay. So because the radar signal create the interference for communication signal, similarly communication signal create interference for radar signal. So we need to take care of them. So these are the challenges. Then AI part should be integrated. Currently we have seen the DL application, AI/ML. Okay. So AI/ML people are also pushing in the wireless communication. That is already started. Okay. People look the channel estimation. So people dumping AI/ML to receiver side. So when you have pilots, then using those pilots, the business they try to improve the channel estimation. So that is happening. So I go to this one. Everyone expecting high throughput, okay, for next generation wireless networks. So like how to define the throughput. So throughput I'm defining in bits per second per square kilometer. Throughput can be categorized as cell density, available bandwidth, and spectral efficiency. Okay. So three parameters are there. Spectral efficiency. What do you mean spectral efficiency? This more number of bits. So if you increase the spectral efficiency, your throughput will increase. For example, you sending the BPSK modulation and you say sending the 64 to PLC signal. Okay. So this one has high data rate. 64 PLC because you can send 8 bits. Okay, in a given bandwidth or given time. Okay. So throughput can be increased by increasing the spectral efficiency. So spectral efficiency you can put either you can put more bits means higher order modulation, or you can accommodate more number of users in the given band. Okay. So that way you can improve the spectral efficiency. Okay. But challenge is there when you have a higher order modulation scheme. So what is the challenge? We need a higher signal. Okay. For BPSK signal, how we report? Either real part greater than or less than. But you have, for example, take the 256 form modulation, 256 form. So how much boundaries are required to report the data? So many boundaries. Then these constellation points are closer. Okay, so that is the challenge. So you have the higher spectral efficiency, but you have a challenge how to get higher spectral. So only higher signal is the requirement for higher order modulation. Then another thing is the available bandwidth. If you increase the bandwidth, throughput can increase. For example, Xenon capacity formula. What is that formula? Some rate proportional to bandwidth into log 1 plus SNR. Okay, so bandwidth will increase, then throughput will increase. So bandwidth you can currently you can see like higher channel bandwidth we are using as compared to 2G or 3G mobile phones. Okay, so higher bandwidth we can get only higher frequency bands. Currently, all these low frequency bands, especially sub 6 gigahertz, like bandwidth up to 6 gigahertz, almost fully occupied. Okay, so that's why in the 5G mobile phones we have a new frequency band that is a millimeter wave, that is around 26 gigahertz. Okay, so like lot of bandwidth is available around 26 gigahertz. Okay. Similarly, people start talking about 60 gigahertz. Okay, so a lot of spectrum is there that we can utilize. Similarly, people start terahertz communication for indoor communication. So a lot of bandwidth is there. Okay. So, but problem is that going higher frequency bands like millimeter wave or terahertz frequency band, that is a challenge. The challenge at high frequency, path loss is high. Okay, we remember that path loss proportional to F square frequency. So if frequency increase, path loss increase. So higher frequency range, your signal cannot travel longer distance. That's why if you can see GSM mobile, they can cover the tower can cover big area. Okay, as compared to currently 5G. 5G towers cover only 500 meters. Okay, or even less. And so these are the challenges. Then another thing is that high frequency bands. This signal that we are focusing, that is cannot penetrate the walls. Even like if you see the terahertz communication, if you just put the hand in front of that beam, communication is blocked. Okay. So that is another challenge, how to take care of that. So which meaning is that line of sight scanning is a requirement. Okay. If you're sending a signal from this room to another room, you cannot send using the terahertz frequency direct. Calls will not pass the signal. So you have to have some kind of mechanism that will take care of line of sight communication scenario. So you have the advantage and disadvantage. So you have to design the system by considering the rate. So that is the idea. Cell density. As I pointed out, cell density, if you remember like wireless communication, especially cell, how to design the cell, initially we learned wireless communication from hexagonal cells. Okay. So in each hexagonal cell, we have a tower. So then what will happening in hexagonal cells, you repeat the resources. So meaning in the time slot of frequency, right? Channel. So reuse of the resource in different cells. Okay. So if you have more cells, then more reuse of the resources. Okay. So cell density, if you can increase, means small cell size. So you can accommodate good number of users for device. Okay. For example, you can consider one cell that can dedicate it for this campus. Okay. Then that can handle the less number of users. If you can design the cell that can handle only this electronics department. Okay. Then another cell you can have for computer department. Okay. Same resource you can deploy in the computer department. So that way you can two volts in the capacity. Okay. So that is ideal. So cell density is high, meaning that throughput is high. Okay. But what is the challenge? You have to deploy more base stations. Then what will happen if cells are closer, then internet issue will arise. Yeah. So handover problem will come. So that thing you also take in. So that way we have to think. You have some trade-off, the bad or good. So we have to go by balancing that. So these are some technology. For example, massive multiple antennas, multiple input, multiple output. So multiple antenna you can deploy at a transmitter and a receiver. So you can have spatial diversity. Okay, so you do the massive. There's massive mining for higher spectral efficiency. How to improve spectral efficiency using the mining? Do you have any idea? For example, single antenna at the transmitter side and receiver side. So they dedicatedly communicate. Okay. For example, I have two antenna here and two antenna at the receiver side. So what will happen? One data you can send from the antenna one, another data, different data. You can send antenna two. Then my receiver will take care of that. Antenna signal separate. Okay. And the receiver side, we have to decode the data from both antenna. Okay. So that is another challenge. You can see that we can doubling the data, but interference at the receiver side is going to increase. So that we need to take it. Okay. But massive MIMO, what is happening? This is one maybe you had channel hardening. Channel hardening means that when you have a large number of antennas, that time channel behaves like a step. So that is a very advantage. So as number of antennas are increasing, complexity is not increasing. That is very good thing. That's why massive MIMO or MIMO technology is an integral part of any generation. Or maintenance. The complexity is not increasing that much. Then, as I already discussed, so I'm just going to this multiple access techniques. What are the multiple access techniques? How to accommodate multiple users in the network. So you have to have some kind of access technology. Either, for example, if you can see here, this whole frequency band I have divided into multiple frequency bands. So called FBM, frequency division multiple access. This band is separately dedicated for one user. This band is dedicated for the next user, and so on. Okay. So this is a multiple access FBM. Similarly, have here TDM, time division multiplexing. So this time slot is dedicated for one user. This time slot dedicated to the like that. So this is the TDM. Then you have a CDM, co-division multiple access. So here what I'm doing, what the disadvantage here, only one time, only one user is coming. Okay. What the disadvantage here, only one frequency band, only one user is coming here. But that need to take care here. All the time, all the frequency, all the user are coming. Okay. But they have a different code. This area is representing a different code. So this code is orthogonal to and this code is orthogonal to another code. So all codes in the CDM are orthogonal code division multiple access. Okay. For example, Hadamard matrix. If you take the entries of Hadamard matrix, they are orthogonal. Those are column. So, what the meaning at the receiver side, if you decode this desired signal, you can get that interference very close to zero. Okay, using orthogonal meaning particular time window, if you create two signals, okay, then multiply the two signals and integrate, then you have a zero rate. Okay, that's the orthogonal. Okay. So that will take care by this one. Orthogonal. Another one is the non-orthogonal multiple axis. So what is the here? At particular frequency or particular time slot, only one user is coming. Okay. So what is the drawback of that? Yeah. Yeah. Drawback is also there. For example, you have a 10 frequency slots, so you can only 10 user at a time can communicate. Okay. 11 user want to access, then you have to wait. Either one user leave or you put some extra resource. You borrow the resource from another base station or the MSC, then you can accommodate that use. Okay. But for multiple access technique, what they did, people thinking at particular frequency value or particular time slot, we can put more users, not only single user, more than one user. For example, 2, 3 users we can put. Okay. So idea is that way we can increase the capacity. Why will increase the capacity? For example, my channel is good. Okay. At particular frequency, my channel is good. For example, channel can support 2 Mbps data. Okay. But I am connecting my IoT device that require very low data. For example, kbps. So you are not utilizing that capacity fully. My channel has 2 Mbps data rate, but I am using for only 1 kbps. Okay. So that is not full utilization. So that is the loss of capacity. So that idea people explore or enhance in the non-orthogonal axis. Another thing is that in the orthogonal multiple axis scheme, latency is high. Why? Because dedicated channel for dedicated users. Okay. But normal no dedication, any user can come. Okay. So that resource, like asking for the resource utilization time, okay. Resource allocation time, you can reduce. So that way you can increase the latency. Oh, sorry, reduce the latency. Okay. That way you can. So I'm just highlighting here how this norma works. So this is the downlink scenario. For example, if you have 2 users, X1 and X2, their data, then I'm allocating different powers, P1 and P2. Okay. So this is the file user and here. So I'm not going to use it. So normal principle is that, for example, single resource, we have 2 users. Okay. Both users have a different power. Okay. Single resource, so we have to separate out the users at the receiver. Okay. So earlier what we are using dedicated time slot or dedicated frequency band. So how to dedicate a frequency band? For example, my user is communicating, my data is going on, for example, 1 megahertz. Okay. So I would put low pass filter, band pass filter at 1 megahertz, and I will remove others. Okay. That clear? Okay. But now what will happen? Here, for example, for particular frequency band, I have 2 users. So if I put the band pass filter, then both users will pass. Okay, but we have to separate out the users. So for separating out the users, we have a different power level. Okay, some users may be near the base station, some users far away from the base station. So some users near, then we can give the less power because losses are lower. Some users far away from the base station, we can give more power. So by distinguishing the power level, we can differentiate the non-orthogonal multiple axis system. So that is the idea. Here I have plotted the summary. So this is the capacity summary of orthogonal multiple axis system, and this is the summary of non-orthogonal multiple axis system. So we can see that summary can be improved even in the non-axis. Okay. So this is another multiple axis technique. There is a sparse fold multiple. So this is another multiple axis techniques. That is a norm only, but in the core domain, sparse fold multiple axis. Okay. So SCMA especially introduced by this report in format. Okay. So I'm not going too much detail. In SCMA, this passport multiple access is very similar to LDS, low density stadium, CTM at the LDS, low density stadium. And this is very similar to CTM technology. Okay. This is currently gauge switching multiple axis. So this is the combination of norma and SCMA. So it is splitting multiple axis. This is people exploring for the 60. That is a part of 60. And this is especially developed by Clark's Imperial College London. So I'm not going detail into the applications. And then you're interested, they will. This is an intelligent reflecting surface based communication. So idea is that here, for example, in our base station, here you have point. So some large building between them, then side path is built. Okay. So what the idea is that if you have some surrounding where you can put some reflecting surface, okay, signal not directly go to the user, signal first go to that reflecting surface, then reflecting surface signal towards the user. Okay. So that is the idea. So this is called intelligent reflecting surface based communications, IRS. IRS is a kind of reflector. Maybe you have seen the reflector. For example, if you put this metal plate, okay, then you bring in the signal, wireless signal, then wireless signal reflect on some angle. Okay, and that some angle is decided by that you have metal plate. But in my metal plate, we can vary at different angles. Okay, so reflection angle I can change. Okay? So that is the idea here. IRS can manipulate that reflected signal at different angles. Okay, if you use that, for example, moving, it can focus the beam like, or it can focus. Okay, so that freedom is there. So what will happen? This kind of scenario, especially where line of sight path is blocked, you can focus your signal via reflected beam. Okay. So this is the IRF based communication. This also part of CC communication, especially on Qualcomm is focusing on this side. Okay. So if you can see that how will increase the sum rate, if you have a number of IRS element N, so if you IRS element means that you have a different elements, small entities, that is individual entities. So if the signal goes in this individual plate element, it will reflect. If you go in this one, it will reflect. Okay. Then what is happening? Reflection angle of all the elements you have to combine. Okay. So that way you can understand if we have a number of IRS elements. So vertically you can improve the signal like this. So these SNR gain is proportional to N square. N is the number of IRS elements vertically, but it has some limitations also. Because when N grows, then channel estimation problem is quite difficult. Okay, even wireless communication, you have to channel, then data transmission, then channel estimation, and data transmission. Okay, so N is grows, then channel estimation time will grow. Then you have very less time for data transmission. So that is also limitation. So this is I'm not going to much detail here. So how mathematically model? For example, this is a transmitter. So channel between IRS and transmitter in HN, and the channel between IRS and the receiver in CN. So this is representing the nth element. So how can we write this? We can write like HN. Then this HN is this one channel. Then response of this IRS element, the response we can model A and E power T. So IRS element response is that the reflection coefficient less than 1. Or then it phase is associated 3. Then my transmitter signal, so that is the CN channel. This is my transmitter signal on the base station or modulated signal length. Okay. Then I can combine this one, HN, GN, AN, GK. So you can think there is a signal channel from this part, impinged, then reflected. So receiver you will get this whole signal. Okay. Then you have n elements, then you can add all n elements. So that is the sum of yn. Then put the value of yn, then HN, AN, then you have this. Now question is like these n elements we want to combine together. Okay, how will combine? If signal is real, there is no phase. Okay, positive real. Okay, so for example 1, 2, then maybe 2.2. So you can add 2 by. Okay, if you have a 1 minus 1, then 2.2. So what is that? Minus 1 cancel out plus 1. So all the elements would have the same thing. Then only we can achieve the maximum value. Okay, so that phase part we have to cancel out. Okay, phase part we have to cancel out. So HN is a complex quantity satisfying channel coefficient. For example, related coefficient. Okay. GN is also complex coefficient. So it has a phase. I will take phase of this one and I will take phase of GN also. Then I will cancel those phases with the help of theta. Theta, put theta and phase is theta and phase is equal to negative of phase of HN plus phase of GN. So that is called coherent function. So this way we can achieve the maximum. Okay. Are getting this one? Channel has phase HN and GN. You can see there HN and G. Okay. If I can select the theta and such that HN and GN phase will be cancelled. Okay. So then you have only the real positive. Then all parts will be added together. You have the maximum. Okay. So that way we can achieve maximum. So matrix form it can be written like this one. G is the channel because you have an n elements. Okay. Then theta is the n by n matrix. Okay. Diagonal matrix. And then if you have a this kind of scenario, signal will go IRS, then signal can also go direct path. Okay, so you have two paths, then you can model like this. So this is the cascaded path, okay, and that is a reflected path, that is a direct path, and then you combine the effective channel at the receiver. So that's just the idea. These are some typical scenarios. There are simplification. Processing and communication part I already discussed. Okay, so this OLPM technology. Okay, how many of you know OLPM? OLPM. Okay, so OLPM, as I pointed out, what is the process to design the transmitter and receiver? You have a transmitter part, you have modulated data, that's a constellation box. Then frequency domain, as I pointed out earlier, we look the channel in frequency. Okay, but really you have to do things in the time domain. Okay, so convert the frequency domain signal to time domain. So we take the IFFT, that is the inverse fast Fourier transform. So that's basically idea. Inverse discrete Fourier transform. Okay, then change signal in the time domain. Then we have the CP cyclic prefix. Then it goes to the channel, then channel output to the cyclic prefix. Okay. Then you convert the time domain signal to a frequency. Okay. So I'm sending signal in frequency domain, receiving the signal in frequency domain. That is the idea. Okay. So these are the steps happening: data, then IFFT, CP, and then digital to analog converter, then wireless channel, analog to digital converter, CP input, then FFT, and then data. Especially when relation is going to the Robert double chain in 1966 and others. Okay, so many people have wondered, but double chain is men who find first patent of the OLPM. So OLPM has certain drawback, as I pointed out earlier, because high-speed communication we have a very high load. For example, bullet trains. Then high frequency communication, millimeter wave and terahertz band. If you go, then this Doppler is very high. Then this underwater communication, Doppler is very high. Okay, so these kind of scenarios, OLPM is not because Doppler is. put it out here. Yeah. So this orthogonal time frequency space OTFS is proposed. Okay. So OTFS will take care of high Doppler and high delay. I'm not going to detail because high Doppler communication scenario, this orthogonality OFDM that is in this term. Okay. You can see that this is ideally should be here, but it's here. High Doppler. So that orthogonality is term. This OTFS invented by this Romani Hadami and Salvoraki in 2010. Okay. He is Hadami and he is the Iranian and currently working in the US. So this is he's running also a technology and especially pushing the OTFS for CC, especially high Doppler communication scenario. So if you want to more details, you can look at this paper, and I think there are some video also. So I'm not going about too much about OTFS. OTFS idea is that you have the OFDM. So put another block that is called inverse simplex finite Fourier transform ISFP, and then transfer the side and the center here the receiving side. Okay. So what is happening? Existing wireless systems, you can put one extra block on the side, extra block in the receiver side, so you can convert OFDM to OTFS. That is the advantage. Okay, so you don't change all the hardware. Okay, so existing hardware you can incorporate to the OTFS. That is right. Okay. So idea is that as I pointed out, channel we can understand in the different term. So Hadani understand the channel in the delay and Doppler. Okay. Earlier channel we understand in the time domain. Then we understand the OFDM channel in frequency domain. Hadani explored the channel in delay and Doppler domains. Okay. So he explored the channel, understand the channel in the delay and Doppler, then he designed the OTFS. Okay. So designing the delay and Doppler domain, we have an advantage. What is the advantage? Because with the 2D modulation scheme, so multi-paths that you can get in, you can resolve. Okay. If you look the channel in time domain, you cannot resolve certain paths. Those who have a same delay. If you look the Doppler only, you cannot or frequency. For example, frequency domain, you cannot resolve the same frequency. Okay. But if you have a 2D grid, you have a more resolution in the delay domain. For example, if delay is the same, then maybe Doppler are different. So column and rows will have. In that way, means good freedoms and day. I'm not going to details, but that is the idea. Then this delay Doppler domain you have to convert. So here you put in the data in the delay Doppler domain in OTFS. That is delay Doppler domain we have to convert finally in the time domain for transmitting the signal. So this delay Doppler domain either you can go through the OFDM, that is another one way. Another way is that directly you can go from delay Doppler to time. Okay. So that is that. This is the satellite and non-terrestrial network people are focusing. So integrated connectivity we are looking. So we are combining terrestrial and satellite communication together to new satellites, HAPS, IIT telecom stations. So drones, then balloons. Maybe you have heard that Google, for example, said so the balloon is the balloon has the communication capability that cannot stay before long time. Similarly, my performance stations, this one. So you have a solar panel here. This is the NASA's. So solar panels, some batteries are there. So you have put the transmitter receiver this one. Okay. And then HAPS can send performance. Similarly, you have seen the drones, small drones. Okay. So small runs you can also use for communication. So that is the then you have a satellites. So all these aspects you have to integrate. Okay, that is called integrated terrestrial and terrestrial. So this is very handy. This is definitely going to process. This is a massive mind, multiple antennas. So I'm not going into much detail, but this is the integral part of any 4G, 5G, 6G. So we can have massive mind millimeter huge potential in the lab, vectors, efficiency, and complexity. And then micro dimension is going to be called scalar. Yeah, so I'm just going to stop here from the time. Okay, I have time so I will leave. Yeah, we have any doubts? Yeah, then interact with that. Yeah. 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 Today, AI will be very important. Yeah. Yeah. How can AI be integrated in the CA? Okay. So the AML we cannot put everywhere in the wireless network. Okay, why you cannot put it? Because for example, BPS modulation. So we have a maximum likelihood for the channel that we can maximum likelihood. So no one can put the maximum likelihood, and that is the best performance. So there is no use putting the AIM. There we can do a conventional algorithms are very good. Okay, but certain application, for example, this visible light communication, the channel is non-linear. Okay, so non-linearity when we do in the math, okay, then the non-linear problems like we have to try to advance. If you remember the input-output relation, wireless communication is governed by the input-output relation of the signal. Okay, so certain scenarios where non-linearity is there, we cannot exactly input-output relation. We have an approximation. Okay, so that scenario AIML can fit. How can it? We can understand this way. One slide. For example, this one transmitter you can put the AIML, okay, and then receiver we can put DL block, okay. Then we can jointly tune or like optimize the transmitter and the receiver. Okay, how will optimize it? Initially, we have a constellation. For example, if you have PSK, you may put at particular plus minus one and plus minus j. Okay. If my wireless channel is non-linear, so DL will not give you plus minus 1 or plus minus j. It will give you 1.02 plus minus j 1.3 like that. Okay, so it can optimize the constellation at the transmitter side, giving the channel. Okay, and then receiver side, my receiver will be improved by optimizing the parameter. So certain scenarios, those kind of scenarios, AIML is good. Okay, not always. Okay. Then I pointed out the channel estimation problem. Okay. Then resource allocation. Resource allocation meaning is that when you have the splitting the bandwidth among the users in the network, or you're splitting the power, okay, among the users. So sometimes what we can do, we cannot have a perfect algorithm. If you have a perfect algorithm, that is also very complex. Okay. So when users are moving, then you have to run that algorithm again, then you have to run the algorithm again. So that practically is not possible. That is because certain scenario algorithm is very complex. Okay? Optimal level. So what you can do, you can use the AI. They can predict, okay, the user behavior, okay, or they can optimize the constellation point power allocation continuous. So that scenario we can do with the AI. Yeah. But there is an infinite community. Yeah. We are using CDMA technology only. No, currently we are using OFDM. Okay, 4G LTE. 5G we are also using the OFDM. That new name is new radio. Okay. So new radio is a little bit more flexible than the 4G LTE. Otherwise, the OFDM is the better. Okay. So most likely this OFDM is also going to be the 6G. Okay, because Qualcomm is the dominating industry. Okay, so this coherent technology they developed the OTFS. Definitely OTFS has good performance, but they have to hire that give money to attend this. So that is also very CDMA is not. CDMA people have these mobile phones to have a CDMA, but there is not. Many 4G and generally these odd numbers like 1, 2, 3, 3, 5G, they are not successful. Frankly speaking, yeah, 4G is very successful. 2G is very successful. Even the other. Okay, and then 6G is more successful than place. 5G is not that much successful. So, thank you everyone for listening and coming here. If you have any question, please send me the email. My email ID is sanjeev.ac@iit.bhu. So if any, you can save the slides for participants. Thank you. Thank you. Thank you very much, sir. In spite of busy schedule, we have